Hey there, science fans! Today we're going on an adventure into the fascinating world of molecules. How? With a powerful tool called infrared spectroscopy, or IR spectroscopy for short. It's like a detective's magnifying glass, but instead of fingerprints, we're looking at the unique vibrations of molecules. IR spectroscopy helps us identify unknown substances, study their structure, and even monitor reactions in real time. It's used by scientists, chemists, and researchers in various fields like medicine, forensics, and environmental science. So buckle up, science explorers, as we delve into the incredible world of IR spectroscopy and unlock the secrets hidden within molecules. Imagine every molecule dancing to its own tune. Each one moves in a unique way, creating a symphony of motion at the microscopic level. That's what's happening at the molecular level. These tiny dancers are constantly in motion, each with its own rhythm and style. Each molecule has a unique set of vibrations, like a fingerprint, that sets it apart from all others. These vibrations are influenced by the molecule's structure and the types of atoms it contains. IR spectroscopy uses infrared light, a type of light we can't see with our eyes but can feel as heat, to make these vibrations visible. Infrared light is part of the electromagnetic spectrum just beyond visible light. When infrared light shines on a molecule, the molecule absorbs specific wavelengths of light, depending on its structure and the types of atoms it contains. This absorption causes the molecule to vibrate more intensely. Think of it like this: different types of swings at a playground swing at different speeds. Just as each swing has its own rhythm, each part of a molecule vibrates at its own frequency. Similarly, different parts of a molecule vibrate at different frequencies when excited by infrared light. These vibrations are like the molecule's dance moves, each one unique and telling a story about the molecule's structure. This absorption of specific wavelengths creates a unique pattern called an infrared spectrum, which acts as the molecule's identifying fingerprint. Pretty cool, right? By analyzing this spectrum, scientists can determine the molecular structure and identify unknown substances. It's like solving a molecular mystery with the help of infrared light. Now let's shine some light on how IR spectroscopy actually works. First, we need a source of infrared light. This light is then passed through our sample, which could be a solid, liquid, or even a gas. As the infrared light interacts with the molecules in our sample, some of the light gets absorbed while the rest passes through. The instrument then measures how much light was absorbed at each wavelength. This information is then used to create a graph called an infrared spectrum. This spectrum is like a fingerprint for the molecule, with each peak and valley telling us something important about its structure. So, by analyzing the peaks and valleys in the spectrum, we can identify the different types of bonds and functional groups present in the molecule. It's like piecing together a puzzle. Remember those molecular vibrations we talked about? Well, there are different types of vibrations that molecules can undergo, and each type absorbs infrared light at a specific frequency. The two main types are stretching and bending vibrations. Stretching is like pulling on a spring. The atoms move further apart and then closer together. Bending, on the other hand, is like changing the angle between two connected springs. Within stretching and bending, there are even more specific vibrations like symmetric and asymmetric stretching and scissoring, rocking and wagging for bending. These different vibrations create a unique pattern of peaks in the IR spectrum, allowing us to identify specific functional groups within a molecule. It's like each vibration has its own signature move. Section 5. Types of IR spectroscopy, from dispersive to Fourier transform. In this section, we will explore the fascinating world of infrared spectroscopy and how it has evolved over time. Just like there are different types of telescopes to observe the stars, there are different types of IR spectrometers. Telescopes come in various forms, each designed to capture different aspects of the cosmos, from radio waves to visible light. Similarly, IR spectrometers have been developed to analyze the molecular world in unique ways. Two common types are dispersive IR and Fourier transform infrared spectroscopy, or FTIR for short. These two methods have distinct mechanisms and applications, each offering its own set of advantages and limitations. Dispersive IR spectroscopy uses a prism or grating to separate the different wavelengths of infrared light like a rainbow. This method has been around for decades and is known for its simplicity and reliability. The prism or grating acts as a dispersive element, breaking the light into its component wavelengths. Each separated wavelength then passes through the sample one at a time, and the amount of light absorbed at each wavelength is measured. This process can be time-consuming, as each wavelength must be analyzed individually. However, it provides detailed information about the sample's molecular structure. FTIR, on the other hand, is like a high-speed camera for molecules. Instead of analyzing one wavelength at a time, it captures all wavelengths simultaneously, providing a comprehensive snapshot of the sample in a fraction of the time. It measures all wavelengths simultaneously and uses a mathematical trick called a Fourier transform to decode the information. This mathematical process converts the complex data into a spectrum that can be easily interpreted by scientists. FTIR is faster, more sensitive, and produces higher resolution spectra than dispersive IR. This makes it an invaluable tool in modern laboratories where speed and accuracy are paramount. It's like upgrading from a magnifying glass to a high-powered microscope for analyzing molecules. With FTIR, scientists can delve deeper into the molecular world, uncovering details that were previously hidden. This advancement has revolutionized fields such as chemistry, biology, and materials science, enabling breakthroughs that were once thought impossible. Section 6. IR Spectroscopy in Action Applications Across Industries. IR spectroscopy is like a Swiss Army knife for scientists. It has tons of applications. In chemistry, it's used to identify unknown compounds, analyze reaction mixtures, and study molecular structures. The pharmaceutical industry relies on IR spectroscopy to ensure the quality and purity of drugs. In food science, it helps determine the composition of food products and detect adulteration. Environmental scientists use IR spectroscopy to monitor air and water quality, identify pollutants, and study climate change. And forensic scientists use it to analyze evidence at crime scenes like fibers, paints, and drugs. The possibilities are endless with IR spectroscopy. It's like having a superpower to see the invisible world of molecules and understand the secrets they hold. Section 7. Deciphering the code. How to read an IR spectrum. Understanding an IR spectrum can seem daunting at first, but with a little practice, it becomes much easier. Let's break it down step by step. Now let's learn how to crack the code of an IR spectrum. This process involves interpreting the various peaks and valleys that appear on the graph, which represent different molecular vibrations. An IR spectrum is like a graph with two axes. The horizontal axis, also known as the x-axis, and the vertical axis, or y-axis, each provide crucial information about the sample being analyzed. The horizontal axis represents the wave number, which is inversely proportional to the wavelength of light. Wave number is measured in reciprocal centimeters, cm1, and indicates the number of wave cycles per centimeter. The higher the wave number, the higher the energy of the light. This means that peaks appearing at higher wave numbers correspond to higher energy vibrations within the molecule. The vertical axis represents the percent transmittance, which tells us how much light passed through the sample at each wave number. Percent transmittance is a measure of the intensity of light that is not absorbed by the sample. When a molecule absorbs light at a specific wave number, we see a dip or a valley in the spectrum at that point. These dips indicate that the molecule is absorbing energy and undergoing a vibrational transition. These dips are called absorption bands, and they are the key to identifying functional groups within a molecule. Each absorption band corresponds to a specific type of bond vibration. Each functional group has a characteristic absorption band that appears within a specific wave number range. For example, OH bonds typically show a strong broad absorption band around 3,200, 3,600 cm1. It's like each functional group has its own secret code, and we're learning how to decipher it. By recognizing these patterns, we can determine the molecular structure and identify the presence of specific functional groups in the sample. This skill is invaluable in fields such as organic chemistry, pharmaceuticals, and materials science. Section 8. Functional groups in IR. Identifying the building blocks of molecules. Functional groups are like building blocks that give molecules their unique properties. They are specific groups of atoms within a molecule that are responsible for its characteristic chemical reactions and physical properties. For example, the hydroxyl group, or OH, is found in alcohols and makes them polar and able to form hydrogen bonds. The carbonyl group, or C=O, found in aldehydes and ketones, is responsible for their distinct odors and reactivity. Each functional group has a unique set of vibrations that absorb IR light at specific wave numbers. By looking for these characteristic absorption bands in an IR spectrum, we can identify the presence of specific functional groups in a molecule. It's like having a cheat sheet to identify the molecular suspects in our sample. Thank you for joining us on this journey through IR spectroscopy.